In this module of the ACI multi-site training, we're going to cover how to connect the multi-site domain to the external layer 3 network. We will cover initially the different type of L3 outs that are supported with ACI. We'll clarify what the L3 out is and what are the characteristics of each type of L3 out. We'll then discuss how to deploy external EPGs associated to these L3 outs, specifically in a multi-site deployment. We'll discuss also one of the typical problems that we have when extending subnets across different data center locations, which is basically the creation of a symmetric traffic path between the distributed data center and the external network. And in the end, we'll cover a new functionality recently released with in ACI and multi-site called Intercital L3 out. And we'll clarify what Intercital L3 out has been deployed for and what are the specific use cases that allows to cover. Let's start discussing what are the different types of L3 outs that we can deploy with ACI. The typical L3 out is usually called the border leaf L3 out that has been supported from the very beginning and it still is the recommended option. It allows to connect WAN edge routers directly to the border leaf nodes and allows to deploy a sort of VRF light and off to allow different VRFs to achieve connectivity with the external network domain. We can support today up to 800 L3 outs and VRFs per border leaf pair. So it scales up also to a significant amount of VRFs. Each VRF will define its own L3 out, one or more L3 out actually, with its own set of border leaf nodes, which are ACI leaf, logical interfaces, which are the interfaces connecting the leaf to the WAN edge routers, and also a routing protocol to be used to exchange reachability information with the external network domain. But this needs to be repeated, this configuration needs to be repeated for each L3 out and hence for each VRF. In terms of functionality, these represent the richest option in terms of L3 out deployment because it allows you to support layer 3 multicast communication in addition to layer 3 unicast, allows to deploy the shared L3 out model where a single L3 out, usually deployed in the common tenant, can be used to provide connectivity to different tenants internally defined inside the fabric, and also allows to provide host route advertisement support, and we will see in a few slides where this host route advertisement becomes important. So this is definitely the recommended option for the L3 out deployment with ACI, and the same holds true when we deploy ACI multi-site. A different flavor of border leaf L3 outs that was released as part of ACI 501 consists in creating an SR MPLS or MPLS end-off on the border leaf nodes. So still we use L3 outs defined on the border leaf nodes. The external WAN edge routers typically are connected directly with the border leaf, but they could also be a segment routing enabled network in between them. And the main difference between the previous approach and this one is that a single control plane session leveraging MPBGP EVPN is used here to exchange reachability information for the prefixes of all the tenant VRFs. And this BGP EVPN peering adjacency allows to carry prefixes for the subnet deployed inside the data center and also MPLS label used to identify the specific VRF the traffic belongs to. This is because from a data plane perspective, all the traffic that is sent out of the border leaf has at least one MPLS tag. If the WAN edge router are directly connected to the border leaf, a single MPLS tag will be present in the packet, identifying the VRF the traffic belongs to. If there is an SR network in between the border leaf and the WAN edge routers, two labels will be used, one for identifying the VRF and the other one used to basically be able to route or switch or forward the traffic across the SR MPLS network. Now, when you deploy this model, only specific WAN edge routers, hardware routers are supported. You see the list here. And from a border leaf perspective, the support is restricted to FX, FX2, and GX leaf models. In terms of functionality, This allows essentially to connect or establish connectivity between data centers or between a data center and remote location across a segment routing enabled network, so that customer can use the typical traffic engineering functionality that they leverage across a segment routing core, and they can also use the typical tools that they use for troubleshooting, for day-to operation, to use in MPLS WAN deployments. In terms of functionality, though, this is less rich than the other one. We do not support today share L3 out, and also we do not support layer 3 multicast communication out of this type of L3 outs. Okay, so definitely the traditional border leaf L3 out is the most feature rich. The third type of L3 out changes a little bit the paradigm, because the external WAN edge router now, they're not connected anymore to the border leafs. In fact, the border leaf nodes are not defined at all, but they are directly connected to the spine. And this takes the name of Golf L3 out. So only specific external router can be supported when deploying this type of L3 out, because from a functional perspective, an MPBGP VPN control plane is established between the fabric, the spines, and this external router. And from a data plane perspective, we use VXLAN to be able to send traffic in and out of the data center toward the external WAN. There is also an additional control plane used here, which is OpFlex, that allows to configure, automate the fabric-facing configuration of the external WAN edge router that are also called the Golf routers. These used to be recommended for large-scale VRF L3 out deployment, but we saw that even with the traditional border leaf, we can scale up to 800 L3 outs and VRFs, right? So we have already a good amount of scale. Some people see advantage in deploying Golf because of the single control plane instead of deploying a VRF Lite with multiple control plane peerings. Now, from a functionality perspective, this also does not allow you to support the layer 3 multicast or a share L3 out, but allows to support host route advertisement. In fact, it was the first flavor of L3 out supporting host route advertisement, which is the main reason why several enterprises deployed Golf in the past or looked at deploying Golf. Today, the recommendation is to go with the traditional border leaf L3 outs, because it's a more feature-rich alternative option to deploy L3 outs, which, let me be very clear, does not mean the Golf L3 outs is not supported anymore or is dead. It's still there, it's still supported. If you have deployed it, we will support you. If you want to deploy it, we will support you. But we strongly recommend you instead to look at border leaf L3 out approaches. Now, no matter which L3 out I deployed, associated to the L3 out, there is one or more external EPGs. The external EPGs essentially represent or model the external destination that can be reached through the L3 out. When deploying external EPG in a multi-site domain, the interesting question comes, should the external EPG be a stretch object or should be an object defined individually at the fabric level? And here, the external EPG, in my opinion, the recommendation is to have it defined as a stretch object every time the L3 outs defined in the different sites. In this example, we have an L3 out in site 1 and a separate L3 out in site 2, provides access to the same external destination, right? So in this example, I have a WAN and I have the two sites connected to the WAN via the local L3 out, but both provide access to the same WAN destination. If that is the case, then I can have an external EPG, a single external EPG defined as a stretch object, which, if you remember the previous multi-site module, means the external EPG must be defined in a template which is mapped to both sites. And then the single external EPG defined as a stretch object is mapped locally at the site level to the specific L3 out defined in that site. Okay, so this is again is recommended when the local and remote L3 out provides access to the same external destination, because it simplifies the policy definition and the external traffic classification. I can define a 000/0 classification subnet for the external EPG, and at that point, no matter if I come in L3 out site 1 or if I come in L3 out site 2, the traffic is going to be associated to that single external EPG. So based on the policy and the contract that I define with the internal EPG, I will then be able to establish or deny connectivity. Okay? However, there may be a scenario where I may also configure L3 outs or create L3 outs to provide connectivity to unique resources. In this example, the L3 out in site 1 give access to a set of resources that are different from the one that are reachable via the L3 out in site 2. In this case, it may make sense to define a separate external EPG associated to each L3 out. In this case, each external EPG can be mapped to the local L3 out either at the global template level or at the site level of the template configuration. Okay? Depending on the traffic flow that I want to establish, for example, in this case, I have a EPG green endpoint in site 2 that wants to talk to the resources accessible by the L3 out in site 1, I may need to enable the intersite L3 out functionality. And we will see what that means in a few minutes. Okay? Normally, I would say this is more rare, right? A dedicated external EPG to the L3 out only is deployed when the L3 out is only defined in a site and provides access only to specific resources from that site. Very commonly, we have the deployment of a stretch external EPG instead. Solving asymmetric routing issues. So what do I mean with this, right? Every time we create a DCI topology, we interconnect data center, and we stretch subnet across data center, we always have the problem of how to optimize the routing between an external client and that stretch subnet or endpoints that are actually deployed in the stretch subnet. You see this example here. I have two sites. Each site has its own L3 out. I define my stretch external EPG because both L3 outs provide access to the same external WAN in this example, and I deploy in each site a perimeter firewall, actually a pair, active standby pair, for each data center to apply security policies at the perimeter of each data center. Right? Each fabric, each site is an independent network, so I have an independent active standby pair in each site. I have my subnet stretch, so one endpoint .10 is located in site 1, another endpoint .11 is located in site 2. Because of this configuration, the same subnet 10.10.10/24 is going to be advertised out of the L3 out of site 1 and out of the L3 out of site 2. I could do something to play with the metric to ensure that, from an external network perspective, I see that subnet as reachable better from a specific site. But let's say I don't do anything, right? If I don't do anything, it may happen that traffic originated by the external client and destined to the .11 endpoint is actually steered toward the L3 out of site 1. If that was the case, the traffic would be received on the border leaf in site 1, and then multi-site will do its job, which is forwarding that flow to whatever fabric that destination endpoint has been discovered. Right? So these represent a suboptimal traffic path because traffic comes in data center 1 even if the destination is in data center 2, but works without any problem. When the endpoint in data center 2 replies, it will use normally the local L3 out to reach the external destination because the local L3 out has a better metric, from a reachability perspective, is closer, quote unquote, closer compared to the remote L3 out. And so, because of that, the traffic will now traverse the response, the outbound flow, will traverse a separate firewall from the one that was traversed by the inbound flow. And this means that the firewall will basically drop the flow because of a lack of connection state. If you think about a TCP connection establishment, the SYN is being seen by the firewall in site 1, the SYNAC is sent to the firewall in site 2, and this will simply not work. So how do I solve this problem? Which is a common problem, as I said, that we have had for 10 plus years, every time stretching a subnet across separate data center. Solution number one is by enabling host route advertisement. So instead of advertising a /24 generic subnet out of both data center, I enable this functionality that allows me to send host route, specific host route information out of the L3 out of each fabric. So from site 1 L3 out, I will only advertise the .10/32. From the L3 out in site 2, the .11/32. In order to enable this host route advertisement, I can actually enable this at the bridge domain level on the multi-site orchestrator. For each bridge domain that is stretched between the sites, I can toggle that host-based routing option. Okay? By doing that, by default, I advertise the subnet, and in addition to the subnet, also the host routes for the locally discovered endpoints. Now, doing that ensures that when the external client wants to communicate the .10, traffic is sent to the L3 out in site 1. When he wants to communicate to the .11, it goes to the L3 out in site 2. So I make my in and out flows symmetric, okay? And this will not create any problem with the firewall. The consideration here is that in order to do that, I need to ensure that the host route can be advertised inside the external network, and as a minimum need to be leveraged by the WAN edge routers to basically use them, build then an overlay technology that could be Lisp, GRE, whatever, that allows to leverage this specific host route information to ensure that traffic coming in the data center will always traverse the perimeter firewall of the site where the destination endpoint is actually located. Okay, this works, as we said at the beginning, also for border leaf L3 outs starting from ACI release 4.0.1. Okay, so you need this minimum ACI release to be able to deploy this. A second option to solve the problem is not to deploy independent firewall as perimeter firewall in each data center, but enable, for example, the firewall function only on one site. So I can deploy an active standby pair of firewall. The active is connected, is the perimeter firewall in fabric 1, site 1. The standby unit is in site 2. At this point, the subnet information is only going to be advertised out of site 1 because it's the only active path between the external network and the multi-site domain. And so all the traffic will always be sent via the L3 out of site 1. If the destination is local, it's an optimal path. If the destination is not local, it's a suboptimal path, because I come in the L3 out in site 1 and I need then to send the traffic to the remote site where the endpoint is located. But here another important point comes up, which is in order for the return packet from the blue EPG endpoint to be sent to the L3 out in site 1, we need to enable a functionality that has been released in ACI release 4.2.1, which is called Intercital L3 out. Before 4.2.1, this was not possible, and this model would not have worked because site 2 endpoints could not use the L3 out deployed in a remote site. So what is Intercital L3 out and why we deployed it? As I said, Intercital L3 out requires two things. Required to run ACI minimum 4.2.1 between all the fabrics part of the multi-site domain that I want to enable this Intercital L3 out functionality between, and it also requires an MSO release minimum 2.2.1. To understand why we deploy Intercital L3 out, we need to look at the behavior before 4.2.1. And as I said, before 4.2.1, endpoints located in a site could only use the local L3 out to communicate to whatever entity connected to that L3 out. That could be the WAN, could be mainframes, could be firewall devices, load balancer, whatever connects in L3 out mode to the fabric, whatever peers L3 with the fabric, I would say. Okay? What was not possible was to have an endpoint in a site communicating across the intersite network to reach the border leaf, the L3 out, in a remote site, in site 1, in this example. Okay? And this limitation applies to border leaf L3 outs and golf L3 outs. Okay? Before ACI release 4.2.1, the one on the left was the behavior. Release 4.2.1 and MSO 2.2.1 brings supports for Intercital L3 out. So now we can have an endpoint in a site communicating with whatever is connected to the L3 out over remote sites. In order to enable this functionality, we have to do two things. First of all, we have to ensure that external prefixes learn from the L3 out in a site were exchanged across sites. And in order to do that, we added to the EVPN adjacency that already exists between spines of fabrics that are part of the same multi-site domain, we added a VPN-v4 or VPN-v6 peering to be used to basically communicate external prefixes across sites. The second thing we had to do, we changed the way that inter-site VXLAN encapsulation works, specifically for these flows. Instead of establishing a tunnel between a local leaf, in this example the leaf in site 2 where the endpoint is connected, and the spine in site 1, and we saw that all inter-site communication normally happens like this because the receiving spine needs to perform the namespace normalization function. Okay, here we establish a direct tunnel between the compute leaf where the endpoint is connected in site 2 and the border leaf that provides access to the external domain in site 1. Now, in order to be able to deploy this direct tunnel, we had to do something, right? Why? Because the TAP address, which is associated to the ACI leaf, by default is assigned from the original TAP pool that was configured during the fabric bring up. Now, we didn't want to assume that this routable original TAP pool was actually routable across the inter-site network. And very often, in fact, we have customers that may want to put together fabrics that have overlapping TAP pool defined. Okay? So in order to be able to build consistently a direct tunnel leaf to leaf across independent fabric, we had to introduce the concept of a routable or external TAP pool, which is an additional prefix that is added to each fabric, and the border leaf TAP are assigned out of this new pool. This is beneficial because it allows me to choose which pool to use, which subnet to use, to assign a TAP address to the border leaf, and so I can ensure that I pick one that can be routed across my inter-site network infrastructure. Okay, so these were the two functionality that were added: the control plane between the spine, the VPN-v4, VPN-v6 control plane, and the routable TAP pool configuration. What kind of use cases does Intercital L3 out supports? The one we already discussed, where an endpoint in a site communicate with the L3 out of a remote site. On MSO, in order to allow this to happen, I will apply a contract between my blue EPG in this case and the external EPG. Okay, and this will allow that communication to flow as you see here, actually in the two directions. Okay, and this could work intra-VRF and can work inter-VRF. A second use case that can be supported is a transit routing use case where traffic between different L3 outs deployed in different sites can be supported intra-VRF, inter-VRF. So in this use case, the multi-site domain performs a distributed routing functionality that allows to external layer 3 network, one connected to the L3 out of site 1 and one connected to the L3 out of site 2, to communicate with each other. Obviously, in order to enable this connectivity, I now need to apply a contract between the external EPG associated to the L3 out in site 1 and the external EPG associated to the L3 out in site 2. So, few more details about this inter-site L3 out functionality. As I said, we need to introduce the routable TAP pool for this to work. That routable TAP pool it's a prefix that can be configured on MSO as part of the infrastructure configuration. You will find a routable TAP pool field that allows you to specify a prefix that can be /22 to /29 size. If you were to assign a /29, which is a small subnet, and you were to exhaust all the addresses in that pool, then at that point you will be able to add another TAP pool, right? So these are additive, they don't need to be adjacent, they can be completely independent subnet, and so you can add as many routable TAP pool as you want. And every prefix that is reachable via the L3 out of site 1 will be learned in site 2, with the next stop being the border leaf routable TAP address, which is a loopback, which is assigned out of that new routable TAP subnet that you have configured. We also had to add, as we said, a control plane. The control plane that we added is a VPN v4, VPN v6 peering between the spines. So it's another address family in addition to the EVPN peering that we already have between the spine to exchange internal endpoint reachability information. So when a prefix is learned in an L3 out of site 1, first that prefix is going to be distributed using the VPN v4 peering inside the site. So all the leaf always peer with a pair of route reflectors that are deployed on the local spines. This allows all the local leaf where that VRF is deployed to learn about this external prefix. In addition, because of that intersite VPN v4, VPN v6 adjacency, the prefix is also sent to the remote sites, to all the remote sites where that VRF is deployed. And the information that is communicated is, first of all, the prefix, okay, the external prefix, the subnet that is reachable via the L3 out, with the next stop to reach it, which is the border leaf routable TAP address. In addition to that, we also add the information of the L3 VNI that needs to be used when by the compute leaf when you encapsulate the packet and send it across sites. Why do we need this L3 VNI information to be sent? The answer is because there is no namespace translation that is applied anymore on the on the spines of the receiving site. Why? Because the traffic is directly encapsulated leaf to leaf, as we said before, right? So the spine in the receiving site where the L3 out is defined cannot do any namespace normalization. They just route that IP packet toward the local border leaf. And because of that, we need to ensure that when the compute leaf inside 2 encapsulate the packet, it puts in the header, the external header, VXLAN header, a proper layer 3 VNI information which identifies the VRF that is connected to the external network, and that L3 VNI needs to represent the VRF inside site 1, not inside site 2. So the border leaf inside 1 needs to communicate to the leaf inside 2, okay, this is the L3 VNI that means this VRF for me, please use this when you send, when you encapsulate the packet. This is a mechanism that we call downstream VNI assignment, okay? Let's put this then everything together and see how the communication end-to-end works. So I have an endpoint inside 2 wants to communicate with an external prefix P1. He sends a packet destined to P1. The local leaf, first thing it does, it derives the class ID of the destination based on a locally installed external prefix. So it's able to apply the policy right there, right? So as I told you before, in order for this endpoint belonging to the EPG to talk to the external world, I need to have a contract between the EPG and the external EPG, right? Based on that contract, the traffic here will be allowed, denied, redirected. I will do whatever I need to do, okay? Now, I apply that the policy, and then I encapsulate the packet to the destination border leaf tab that advertised the prefix originally, using the specific L3 VNI value in the VXLAN header that was specified in the control plane exchange. The packet is then directly encapsulated to the destination border leaf. However, when it crosses the local spine inside 2, one of the local spine, that spine, like it always does for any intersite communication, is going to change the source IP address in the external VXLAN header so that the packet will look like source from the overlay Unica step address which identifies site 2. The receiving spine will not do anything, will just provide routing toward the border leaf TAP address. When the packet gets to the border leaf identified by the routable TAP address, the border leaf decapsulates the traffic using the L3 VNI knows in which VRF to perform the lookup, and then we'll send the packet toward the external destination. One important point to clarify is that the remote endpoint learning information is disabled on the border leaf, so we'll never learn specific endpoint information for the endpoint on the border leaf in site 1. Why? Because not having the namespace normalization function, we cannot assume that the class ID for the endpoint in site 2 has any meaning in site 1, right? So there is no federation between these two fabrics, and so that class ID it's meaningless in site 1. So we avoid at all the problem by not learning the endpoint information on that border leaf. which basically means when the external client communicates, sends the traffic back destined to the endpoint, the packet gets to the border leaf. The border leaf doesn't have specific endpoint information, so it will basically send the packet to the local spine, following the proxy path. The local spine will look in the kube database, and assuming the endpoint has been discovered, which is obviously the case in this example, will be able to encapsulate the packet to the site, to the overlay unica step address identifying the site where the destination endpoint is connected. The local spine inside 2 will receive the packet, perform its namespace normalization function, and then forward the packet to the leaf that will apply the policy and then forward the packet to the endpoint. So from this direction, right, from site 1 to site 2, is basically normal multi-site forwarding. The enhancement were needed to handle the opposite direction, from site 2 to site 1, where we establish the direct tunnel between leaf nodes. Last point I want to cover is some of the restrictions that we currently have with multi-site and inter-site L3 out. First of all, is only supported with the VRF flight and off border leaf L3 out. So no golf, no SR and PLS. Okay. Is also not supported when I have an endpoint connected to a remote leaf pair associated to site 1, and the L3 out is defined on a remote leaf pair associated to site 2. Okay. This traffic flow is not possible. There are also some specific multicast restrictions that will be covered in a different module of the multi-site training. But the most important restriction, current restriction that I want to call out, is the fact that site-to-site cloud-sec encryption cannot be used when I enable inter-site L3 out. The two functions are incompatible with each other, right? And not only for the flows, for the inter-site L3 out flows, but also for regular endpoint-to-endpoint flows, the cloud-sec encryption is not supported if I enable inter-site L3 out. We will support this in an upcoming MSO and ACI release, but as of ACI 502 and MSO 302, these two functionality cannot be enabled together. This ends this module of the multi-site training. I now pass the ball to Joe that will show us all this concept in action in his lab. Thanks for watching.